Hello and welcome. This is our next video lecture 8.2, and the reading in the book is Chapter 8, Section 2, Conservation of Mechanical Energy. That's a pretty impressive title for a section, and in fact it represents our first example in this class of what is called in physics a conservation law. Now, that word conservation, used somewhat frequently in everyday life, what does it mean specifically in physics? Well, in physics, a quantity is said to be conserved when its value is constant. Okay, so in physics, it's quantities that are conserved. The quantities in physics that we've already defined and introduced, and under certain set conditions, the values of those quantities don't change with time. They are constant. Okay? So in physics, to say something is conserved means its value is constant, does not change. Why is that important? Because that's a pretty severe constraint on the behavior of a system. If it must behave so that the value of some quantity never changes, that can limit what you can observe. And it can help you predict what's going to happen in the future. In fact, it can help a lot, as we will see. So what we're going to try to spend a good bit of time on our first conservation law is explaining very clearly what is specifically is the quantity that is being conserved, what is it that's conserved, and two, what are the conditions that have to be true before that quantity is conserved. Okay, we have to be clear what is being conserved and under what conditions it is being conserved. Then, and only then, step 3, we can use this so-called conservation law to help us predict the future behavior of something. And what that means for us in a very pragmatic sense is it will help us do Wiley plus problems. All right, so apparently in our first example of a conservation law, the thing that's going to be conserved is a quantity called, let's be clear, mechanical energy. So what we have done so far is introduce energy in two forms. The first form we introduced was kinetic energy. The energy a particle had merely because it moves, and that kinetic energy was defined to be 1/2 times the mass of the particle times the magnitude of its velocity squared. That's hopefully our old friend by now. K equals 1/2 m magnitude of velocity squared. Then the next form of energy we introduced was called potential energy. And that actually came in two separate forms, because you have to have what's called a conservative force doing work on your particle. And there are two conservative forces, the gravitational force and the spring force. And for each conservative force, there is a corresponding potential energy function. So we have two forms of potential energy, gravitational potential energy and elastic or spring potential energy. And we had a formula for each. All right, now we're going to introduce a new form, a third form of energy. And it's just going to be a definition, okay? And it is called mechanical energy. Here comes the definition then of the mechanical energy of a system. Note the definition and note the symbols we use. The symbol we are going to use for mechanical energy is a capital E with a subscript MEC. Here's the first time actually we use the symbol E for energy, isn't it? Well, that's the way we're going to do this. Mechanical energy will be denoted E subscript MEC. We must use this notation. Otherwise, we're all talking different languages and we're going to get all confused. So here's the definition of mechanical energy. Note 3 lines. This is the definition. It is the sum of the kinetic energy of the system plus the total potential energy of the system. Kinetic energy of the system plus the total potential energy. And all we mean by total potential energy is take however much gravitational potential energy the system has, plus however much elastic potential energy the system has. Okay? All right, so that's just a definition. That is the definition of mechanical energy. In and of itself, that definition is of no interest. What makes it interesting is the next idea. That is, that there are conditions under which the mechanical energy of a chosen system will be constant, i.e., will be conserved. And that's what we have to really focus our thinking on and understand. Under what conditions does the mechanical energy of a system not change? Please note this notation. Delta, remember delta in front of any symbol means change in. So delta E mech means we're talking about the change in the mechanical energy. And so with that little formula that I just circled in red, I'm talking about the conditions under which the mechanical energy of a system does not change, right? The change in the mechanical energy equals 0. We need to be very clear about what those conditions are, because that's when those conditions are satisfied, that's when the mechanical energy of a system will be conserved, i.e. constant, and then we can use that fact to predict future behavior and solve problems. All right, now, one of the things I'm going to spend a good bit of time talking about, both in the remainder of this video and in our class sessions together, is the importance of being clear on what we mean by our system. We have to pick it. We have to pick the system. And we have to be clear on what we've picked the system to be. Okay? So let's be upfront and say, we're going to have to pick a system. I'm going to talk about how you go about doing it, okay? But we're going to have to pick a system. That's got to happen really pretty much first. Then you look for the next two bulleted items. If they're both valid or true, then the mechanical energy of that system will be conserved. Here are the two conditions. There must be no external forces doing work on the system. No forces. Remember, that's why you have to pick the system. You got to know what it is. Then you can say, are there any external forces, any forces from outside the system doing work? That would be written in symbols this way. W for work, subscript ext for external. External work equals to 0. There can be no external work done on the system. There can be no external forces doing work. By the very meaning of work, if there are external forces doing work on a system, then energy is being transferred into or out of that system. Okay? So there can be no external forces doing work on the system. That's condition 1. Condition 2, of the internal forces doing work. Whoop, sorry, I want that to be on highlight. Of the internal forces doing work, they must all be of the special kind called conservative forces. The only internal forces doing work are conservative forces. And remember, we only have 2 conservative forces so far. The gravitational force and the spring force. Okay, so again, the 2 conditions are no external forces doing work, and of the internal forces doing work, they must all be conservative. If those 2 conditions are met, then the mechanical energy of that system as we chose it will not change. And we can use that fact to predict future behavior. I can tell you a couple of important things up front. Okay? First, one, there can be no sliding, rough, internal surfaces. Okay? No kinetic frictional force on internal surfaces. If that happens, if you have any internal surfaces moving against each other and they're rough, so that there's kinetic friction between them, that's it. Mechanical energy conservation is gone. And I'll tell you why later on in the chapter, but the bottom line is If there are rough surfaces sliding against each other, kinetic frictional forces on the internal surfaces, you're generating what we're calling thermal energy. Now, we haven't defined that formally, but you know intuitively, I suspect, what I mean by thermal energy. And if you want an example of generating thermal energy, just rub your hands together, hard, vigorously. And you have rough surfaces sliding against each other. There's kinetic frictional forces between those surfaces, and you're generating thermal energy, and your hands feel that. Okay? That's it for mechanical energy conservation. It's over. It isn't happening if there are kinetic frictional forces on the internal surfaces. So that's one deal breaker for mechanical energy conservation. Kinetic friction. All right. Let me talk a little bit more about, let me give you some of my important ideas about picking the system. Okay? All right. Give you some guiding ideas here. Choosing a system. I'm going to be coming back to these ideas. First of all, there's going to be a particle we're going to focus on. And in almost every problem, it's going to be very straightforward to identify what the important particle is. So that's kind of the first thing. Focus in on whatever the particle is. Block, stone, something. Okay? Then, yes, we still need a free body diagram for the particle. Okay? For the particle. Why? I need to know the forces acting on the particle. Why? I need to see if any of them are the special ones, conservative, or if there's kinetic friction. I need to know if there are any conservative forces acting and doing work, and if there's F kinetic. And then after you know which forces are acting and doing work, that will help you choose the system. Right? And basically what happens is, if you have the gravitational force doing work, choose the system to be the particle plus Earth. If you have a spring force doing work, choose the system to be the particle plus the spring. Okay? All right. That's gonna be kind of our guiding principles. And I think the best thing to do after you kind of just state these ideas is dive right into applying them, because that's really the only way we're going to develop an understanding, is to see that we can use these ideas correctly. So I'm going to do a kind of a mini example, not with any real complicated calculations, but more about ideas here. Then I'm going to leave you with a class engagement exercise for this video, and then we're going to be doing some example Wiley Plus type problems in class. All right, so let's go to this mini example. We're going to practice applying this idea of conservation of mechanical energy, and how we go about doing that systematically. It must be done with care. So here is the scenario. Our particle in this case is a stone. It's got some mass m, and it's placed on a vertical spring with spring constant k. And of course that will compress the spring. So hey, we've got a picture over there. So you can hopefully imagine that. It's some kind of a spring that's set up vertically, attached to the floor at one end, and it's got a little place on the top for the stone to sit. And it's one of those kinds of springs that can be stretched or compressed. In this case, it's going to be compressed. And of course, every spring is fabricated to have a natural length. I'll call that L. That's the length it will be at if you don't do anything to it. It's equilibrium length, or it's unstrained length is probably a better way to say it. All right, so all we're going to do is set up that vertical spring. It's got some spring constant, some stiffness, little k, and put the stone of mass m, and for now, just let it rest on top of the spring. I hope you can visualize that the stone will just sit there in equilibrium. There'll be a downward force due to gravity, and if it's sitting there with no acceleration, there must be an upward force to balance F grav down. What would that upward force be? Be the spring force, wouldn't it? And when we're in equilibrium, the spring is compressed just enough so that the spring force up is just enough to balance F grav down on the stone. Okay, and of course, it would sit like that forever, and that's pretty boring. So let's do something a little more interesting. From that equilibrium situation, let's push down on the stone and compress the spring a little bit more. All right? From equilibrium. Just push down on the stone and compress the spring just a little bit more. And then all we're going to do is let go. Not going to push on the stone ourselves. We're just going to let go. Release it from rest. Okay? We all know intuitively what's going to happen. The spring force is now greater than the gravitational force. The stone will start to accelerate up. Okay? Okay, but now, and it's going to go up. We'll talk about all that in a minute. But for now, what I want to do is I want to take this picture, and I want to be clear about what I'm visualizing this picture to be. Okay? Our starting scenario is when we have compressed the spring more beyond equilibrium so that the stone is a height h above the ground. And I'm going to take that to be this picture right here that we have. Okay? That is to say, think of the stone as a particle. Its height h above the ground, its height above the ground is little h. Okay? So that's where I'm holding it, and I'm just going to let go. All right? We are told in this problem to take this very picture we've got to be the reference point for the gravitational potential energy, i.e. U grav equals 0 when the stone is right there at height h above the ground, and I have just let go. That means I think it's going to be very important to put into our picture a plus y-axis going up, and to denote where y equals 0 must be. It must be there because of what the problem told us. The problem told us to take y equals 0, and therefore u grav in this picture, I'm going to call this picture 1. We will take u grav equal to 0 when the stone is height h above the ground. Okay, so this is my picture 1. Let me add one other thing to the picture. I just let go of this stone. I released it from rest. So its velocity at this moment, when I just let go in picture 1, height h above the ground, its velocity is 0. Okay, that's our starting situation. Part A of this practice problem asks, for what system is the change in the mechanical energy equal to 0? Pick a system, tell us what it is, for which the mechanical energy is conserved. All right, first of all, we have to identify what's the important particle in the problem that's moving around. It's going to be something in any problem we're given. In this case, it's the stone. That's the particle. So what are the forces that are acting on the stone? We already mentioned them, right? There's F grav down and the spring force up. So those are the two forces acting on the stone. Now, if your head's thinking, wait a minute, aren't there other forces? That's fine to think about that, but let's think about it ourselves now. Are there any other forces acting on the stone? If there are, you have to be able to tell me what's the physical agent that is directly pushing or pulling on the stone. If you want to call, if you're wanting to say the normal force from this little surface thing right here, that's the stone. Okay, that's the stone. So that's the spring. That's the spring force. So we've already accounted for that. It's not on a surface, so there is no normal force. The only forces acting on the stone are F grav, gravitational force, and spring force. And yeah, we're going to neglect air resistance when it's moving. Note that they are both conservative forces acting. F grav and F spring are the special ones, conservative forces. And yes, they're both doing work. So I have a particle that's a stone, and I have two conservative forces doing work on it. So that tells me what to pick for my system so that I have mechanical energy conservation. You always start with the particle, but there's going to be more. Plus, as I mentioned a few minutes ago, if the gravitational force is doing work, the agent is then Earth. So include Earth in the system, because technically the gravitational potential energy is shared between the particle and Earth. If there is a spring force doing work, also include the spring. And that's what's going to be our system. If that is our system in this case, then the mechanical energy of this system cannot change. Delta E mechanical equals 0. Because the two conditions up there at the top of the screen are met. There's no external forces doing work because I've already included Earth and spring, and those are now internal forces. And of the internal forces doing work, they're both conservative. So the conditions for mechanical energy conservation are met. The mechanical energy of this system, stone plus Earth plus spring, will not be changing throughout the motion. Okay, that's part A then. That's the system for which mechanical energy is conserved. Now let's go on to B. Give myself a little bit of room here. A little bit more wording in the problem. It says when you let go, the spring shoots the stone upward to some maximum height, big H, above the ground. I think you can visualize that. Okay. Now let's go on to part B. B. Just as you let go, in other words, picture 1 right there that I've already sketched, because that's what represents where I just let go. Which forms of energy are not 0? And they list 3. Gravitational potential energy, spring potential energy, and kinetic energy. Which ones are not 0? Actually, what I'm going to do is I'm going to go one by one through each of them and state whether they're 0 or not. I think that's the most definitive way to answer it. So let's start with U gravitational. Please remember the formula for it. Mass times G and times Y coordinate. Please say that in your head 3 times. U grav is mass times G times Y coordinate. M, G, Y coordinate. M, G, Y coordinate. Don't say height. Say M, G, Y coordinate. Trust me. Okay. That's why I needed to draw the y-axis and state clearly where the origin is on the y-axis, because this formula has to be used correctly to get U grav. So, basic question here for this form of energy, U grav, in the picture 1. Is it 0 or not? If you need to pause and think about that, that's fine, but I want you to answer it for yourself first. Okay, did you say that the gravitational potential energy of this system in picture 1 is 0? Because we chose the origin on the y-axis at that location for picture 1. There's no U grav. Done with U grav. Next, U spring. When, let's be clear about this, when do we have elastic potential energy in a system? The answer is very clear-cut. When we have a spring that is either stretched or compressed from its natural length. When you have a spring that is either stretched or compressed from its natural length, you have elastic potential energy, US. So now, ask yourself, in picture 1, is the spring stretched or compressed from its natural length? I want you to answer it. If you need to pause the video, that's fine. Did you say yes? In fact, the spring is compressed from its natural length. I mentioned a little while ago, let's say that the spring's natural length is L. We clearly have compressed it to get to picture 1. Its length now is H, and H is less than L. Yes? We have compressed the spring. So, U spring is not 0. To be more specific, U spring is a number that is greater than 0. And to be even a little more specific, I'm going to write down the formula for it. For the elastic potential energy in symbols, This is also an important formula for this chapter. You just need to have it in your head. The formula for elastic potential energy is 1/2 times the spring constant, little k, times the amount of stretch or compression squared. The amount of stretch or compression squared. If its natural length is L and its new length is H, the amount of compression is L minus H, and that quantity would get squared. That's the formula for calculating U elastic in this case if I asked you for an actual number. All I needed to know now is there is elastic potential energy. It's not zero. Lastly, I'm asked in picture 1 if the kinetic energy of the system is zero or not. Again, I would like you to answer that for yourself first. Feel free to pause the video if you need to. Did you say that the kinetic energy in picture 1 is zero? Why? Well, because the formula for calculating kinetic energy is 1/2 mv squared, but our picture 1 clearly shows that the v is zero. There is no motion. It's at rest the moment I let go. Okay, so I have one form of energy only. I have elastic potential energy in a compressed spring. Okay? Now, that's the situation right after I took the stone from equilibrium, compressed the spring a little more so that the stone is height h above the ground, and just let go. That's picture 1. All right, let's go on to part C. When the spring reaches its unstrained length, its natural length L, the stone leaves it. It's not tied to the spring in any way. It will lose contact with the spring. The spring will stay at its natural length L, and the stone will keep on moving upward. That makes sense? So the stone will continue to move upward. Just as the stone leaves the spring, which forms of energy are non-zero? U grav, U spring, and kinetic. Okay? All right, so I'm going to draw a new picture. I'm going to call it picture 2. We're going to be doing a lot of this kind of double picture drawing, sometimes triple picture drawing in applying conservation of mechanical energy, because I need to keep track of what's happening at different times. So picture 2 now represents the situation that is described in part C of the problem. So there's the ground. Let me draw the spring. The spring is now unstrained. That's the fancy way we say it's neither stretched nor compressed. That means its length is L. Remember I said its natural length is L? Okay, and the stone is right there at the top of it at that moment, about to leave contact, and definitely traveling upward with a velocity v. Yes, it's moving upward. Let me also denote where we started. Roughly, I'm just going to say, just for the sake of the picture, that's where we started, okay, when the stone was height h above the ground. Now the stone is higher, yes, at L. Remember the y-axis, plus y up. Remember where y equals 0 is. Can't change that in the middle of the problem. It's at height h above the ground. So now, what's the y-coordinate of the stone in picture 2? y2. Well, I don't think it's too hard to see that that's L minus h above the origin, right? L minus h above the origin. Okay, that's my picture 2, showing what's going on at the moment in the problem in part C. The stone is just about to leave the spring. The spring is at its unstrained length L. The stone is above the height little h where we let go, and it's traveling up. All right, now we go down the forms of energy one by one, and we identify whether they are equal to 0 or not. Let's start with U grav. Is it equal to 0 or not? Answer that, please, for yourself. Pause the video if you need to. Okay, well, did you say, well, the formula would be mgy, in this case it'd be the y2. The whole point is that the y2 is not 0. In fact, it's greater than 0. It's above the origin. So I have non-zero gravitational potential energy. I have positive gravitational potential energy because my particle is above the chosen origin. That's that. That's U grav. What about the elastic potential energy, US? 0 or not 0? Did you say that the elastic potential energy is 0? Because here I have a spring that is at its natural length, neither stretched nor compressed. Remember, you have to be able to identify when you have elastic potential energy. When you have a spring that is either stretched or compressed from its natural length. This spring is at its natural length. No elastic potential energy. Lastly, kinetic energy. K, 0 or not 0? Well, did you say, well, there's a formula for kinetic energy. 1/2 mv squared, all depends on if there's a v, a velocity. This stone is moving. It's moving upward at the moment of picture 2. So absolutely, I now have kinetic energy. Note the formula over here I could say for U grav, mg, and for y2, L minus h. So, depending upon how much information I was given, I could be thinking about comparing pictures 1 and 2. And what I know between the two pictures is that the mechanical energy of the system can't change from picture 1 to picture 2. So however much mechanical energy the system had in picture 1, E mech 1, that must equal the mechanical energy it has in picture 2, E mech 2. That makes sense? Now in picture 1, I discovered that the only form of energy that I had was elastic potential energy in a compressed spring. So all I have in the first picture is U spring, so US1. In the second picture, I have two forms contributing to the mechanical energy: gravitational potential energy and kinetic energy. So here I would write K2 plus U grav 2. So what we have done, in essence, in terms of energy transfers, is we have converted what was elastic potential energy into a combination of kinetic energy and gravitational potential energy. Okay? All right, now there's just one more part. There's no complicated calculations in this problem. Part D up here. Let me get down here so you can see all of it. Part D says, when the stone reaches its maximum height, capital H, yes? Because the stone's going to leave the spring when the spring's at its unstrained length, but the stone still has velocity upward, so it's going to rise, but of course from the gravitational force, it's going to slow, and it's going to reach a maximum height, capital H, above the ground, where for one instant in time, it will be at rest. We are to look at that highest point. And when it's at that highest point above the ground, identify which forms of energy are non-zero: U grav, U spring, and kinetic. So let me draw a new picture. I am running out of room, so I am going to, bear with me, clear some space up in here so that I can draw a new picture. I'm going to call it, for lack of anything more creative, picture 3. Okay? And that's going to enable me to do part D. Very important to draw a picture for each particular part of the problem. Now, picture 3 has to depict what's happening in part D of the problem. Part D, I have an uncompressed spring of natural length L. I have a stone that has gone on upwards and has reached its highest point above the ground, where it is momentarily at rest. That height we are told to call capital H. And since it is momentarily at rest up here at its highest point, its velocity is 0. Okay, now let's add another little bit here. Let's add our y-axis, plus y upward. Let's remember where y equals 0 was, because we can't change that. It was down here when the stone was a height little h above the ground. That's y equals 0. Our stone is now up here at a y coordinate that I'll call y3. And what is that y coordinate? Well, how far is it above the origin? I think it is at big H minus little h. Okay, so that I think is a detailed enough picture that will enable us to answer part D. So let's go one at a time through the 3 forms of energy it talks about. U gravitational. Is it 0 or is it not 0? Think about it, please. Did you say, well, the formula for calculating U grav is m times g times y. So this would be y3. That's m times g times big H minus little h. They're all positive quantities. So U grav is non-zero. It is greater than 0. It is positive. Okay? All right, what about elastic potential energy? U spring, 0 or not 0? Did you say, well, I look at picture 3 and I see a spring that is neither stretched nor compressed. So U spring is 0, easy. What about kinetic energy? K for the system in picture 3, 0 or not 0? Did you say, well, picture 3 shows, at least for this instant that picture 3 represents, V is 0, it's at rest. So the kinetic energy is 0. So the only form of energy we have now is gravitational potential energy. And in fact, I could use conservation of mechanical energy to say that whatever mechanical energy the system had, say, in picture 1 or picture 2, but I'll pick 1, must be the same value for the mechanical energy in picture 3. Mechanical energy is conserved. It's got the same value at all times. In picture 1, it was all spring potential energy, elastic potential energy, US1, remember? And now the mechanical energy is all gravitational. So this says, between pictures 1 and 3, that we have simply converted elastic potential energy into an equal amount of gravitational potential energy. And if the problem gave us numbers, we would be able to calculate things like, what is that highest point, capital H? Or how fast was it going V in picture 2? All kinds of questions like that can be asked if we give you enough numbers. And then you apply these ideas correctly. Okay, so that's a practice I've done with you. So now I want you to do, I'm going to tell you about a class engagement exercise I want you to do. So this will be one where I will create the assignment on Blackboard. Hopefully I won't forget. Feel free to remind me if I do. And you will upload, just type in your answers to this class engagement exercise on Blackboard. Okay, so let me write that down. Class engagement on EB, Blackboard. Here's the scenario. It's kind of like a simplified version of a toy roller coaster. In this figure, we have a small, initially stationary block. There it is. It is released, released, that means you know its initial velocity is 0, on a frictionless ramp, okay, that's important, at a height vertical of 3 meters, right there, above what is presumably the ground or floor. We have hills on the roller coaster, and the heights of the hills vertical above the ground or floor are given, right? First hill has a height of 0.5 meters above the ground. Hill 2 is a height of 1.5 meters. Hill 3 is a height of 2.5 meters. Hill 4 has a height of 3.5 meters. The tops on each hill are nice circles, half circles, okay? And they're identical. So the half circles on each hill have the same radius. And the block never flies off the top of any of the hills that it crests. Now we're going to come 4 questions. A, B, C, and D. Or 1, 2, 3, and 4, whatever your preference is. First, A. Which hill is the first that the block cannot cross? B. What does the block do after failing to cross that hill? C. Of the hills that the block can cross, on which hilltop is the centripetal acceleration of the block greatest? And D, on the hills that the block can cross, on which hilltop is the normal force on the block the least? Is it the smallest? Normal force on the block. You might be served in working out your answer to D in drawing a free body diagram for the block when it is on each hilltop. But to answers A, B, and C, you're going to want to use conservation of mechanical energy. So you first should think about for yourself, what are you going to pick for your system so that the mechanical energy is conserved? And then use conservation of mechanical energy to help you answer A, B, and C. And then use Newton to help you answer D. So that's my explanation of our class engagement exercise, and you will answer that on Blackboard, please. And we will be practicing applying conservation of mechanical energy in class to Wiley Plus problems. But that's all for this video.